Hello again. Welcome to another review session for your final exam in Calculus 3208, presented by CDLI as always. And this time we're looking at ways of estimating areas using Riemann sums, estimating areas under curves using Riemann sums. All right, so new topic related to integration, and we'll see that probably in our next session, how the two are connected together. But let's get at it right now. We're going to look at understanding the area problem and then using left and right hand Riemann sums as ways to estimate the area under a curve. Here we go. Start with a rather simple example here. So this is what the area problem is. When I have a linear function, like this particular one we have graphed over here on the left, versus a nonlinear function, we have two very different situations if we want to find the area that's sort of trapped between the curve and the x-axis. For this first one, since it's linear, what I can do is I can just sort of break my shape down into some known regular polygons, find the shapes of each of those, or find the areas, of each of those, and put them together. So here we'll have a rectangle and a triangle, and we'll get a total area that'll be equal to the area of the rectangle plus the area of the triangle. So for the rectangle, I start at 3 and go up to 9, so I've got a base length of 6. That'll be the same for the triangle. And the height of the rectangle goes from 0 up to 5, so that's going to be 5 units. And then from 5 up to 7 for the triangle makes 2 here. So my areas are going to be, for the rectangle, it's 5 by 6. Use that kind of multiply sign. Plus, for the triangle, it's going to be 1/2 the base, which is 6 units long, multiplied by the height, which is 2. So I've got 30 plus 6, which is 36 units. So no troubles, really, when it's linear. What happens when it's a curved line? Well, when it's in an irregular shape, it's not like we have simple formulas, like length times width or half base times height. So what are we going to do? Well, we're going to kind of find another way to get at this by hook or by crook. So we're going to think maybe we could estimate the area here. We could approximate the whole thing as a triangle and then estimate it. Okay, that's one way to go about it. But what we're going to find is we're going to have a flaw, because all this area in here will be counted, and we don't want to count that. So we'd end up overestimating what we had. So maybe what we could do, and this is another suggestion, is down underneath inside my curve, what if I drew a tangent line that touched the curve like that, found the area of that triangle? Well, that would work too, but it's not going to be perfect because this area and this area will fail to be accounted for. Well, maybe I could average the two, but even then, how close am I to the real thing? I don't know. So what we do is we find a way that won't necessarily give us a better estimate right away, but it'll give us a way to systematize our estimates so that we can figure out a way to improve on them ad nauseum, or to infinity, as we will see. Ad nauseum doesn't mean that, but anyway, it means something grosser. Here we go. All right. So there's a way to do this that's a little more systematic, and it was invented by a guy named Bernhard Riemann. So what Riemann said was, I'm going to draw rectangles under the curve, and then I'm going to take the areas of all the rectangles and add them together. And he said there's two different ways that we could approach that. He said we're going to break the entire interval, so 0 to 1 was the interval we were interested in, into little sub-intervals. Okay, so each one of these down here, like from here to here as an example, is a sub-interval. And on each sub-interval, I'm going to start at the x-axis, and I'm going to draw a rectangle upward until it hits the curve. Well, the question becomes, when you draw your rectangle upward or stretch it upward, do you stop when it first touches the curve? And if you do that, that's the case that we have here, and the first time it touches, it'll hit, in this particular example, at the left-hand corner. So we call this a left-hand sum because the height, or the value we use to determine the height of each rectangle, is actually the height of the function at the left-hand corner of the endpoint, or of the interval, sorry, at the left-hand endpoint of the interval. First day with my new mouth, can't talk very well. All right, so if we don't do it that way, and I'm going to come back to this slide in great detail in a couple minutes, but first I want to peek ahead for a second. If we don't do it that way, let's say we take that same interval, and we're going to draw a rectangle upward, and not until the left-hand corner hits the curve, but until the right-hand corner hits the curve. Then we get this. Okay, and that would be the height of our rectangle. This is called a right-hand sum, and that's the difference between the two. Now with a right-hand sum, if we have an increasing curve like y equals x squared, the example we have here, notice that we're going to get all this extra area that doesn't really belong to what we want, so we're going to end up with an overestimate. Whereas, jumping back again to the other slide, with a left-hand sum, we're missing out on all these little bits here. So we get an underestimate. Neither are going to be perfect. One gives an underestimate, one gives an overestimate, but they'll both give us a pretty good idea. Okay. So if we're going to do a Riemann sum, the first thing we need to decide is how many rectangles will we use? And in this case, we've chosen to use 8. So when I say L8 here, I mean I'm using a left-hand sum with 8 subintervals. So I have to figure out stuff about my rectangles to get all their areas, and then I'm going to add them together, which is why we call it a sum. Okay. So this is the first rectangle would have an area of its length times its width for all of them, yada, 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 until I get to the 8th rectangle. And we should notice something. It's a good idea to standardize our rectangles. It makes it a lot easier if we keep them all the same width. It makes the calculation a lot easier. So what we do is we say we're all going to have the same width. And if there's 8 of them, and the whole interval from 0 to 1 is 1 unit long, I'm going to have the entire width of the interval, which would be like 1 minus 0 from the end to the start, divided by the number of rectangles I have, which gives me a width for all the rectangles of 1/8. So each of these rectangles, the bottom of it is 1/8 of a unit wide, as we stretch from 0 to 1 for x. And we sometimes consider those to be a little change in x, because it's just a little interval of the x-axis, a little subinterval. So we sometimes call them delta x. All right, so let's get down to the nuts and bolts. The width of each rectangle is going to be 1/8. The height is going to be determined by the value of the function y equals x squared at the left-hand endpoint of each subinterval. Okay, so let's see if we can put that together. The first height I'm going to get for this particular example is going to be the height I get, or the height of the curve at 0. So to get that, I'd have to find f of 0. The second height I get is going to have to be f at 1/8, because if each one is 1/8 of a unit wide, and I jump to the other end to get to the next interval, it's going to be at 1/8. So the next one logically is going to be what I get when I evaluate the function at 2/8, 3/8, etc. But for a left-hand sum, the last point that I use in this particular example will be at x equals 7/8. I don't actually get to the other end because I don't have a rectangle whose height gets me all the way up to here. So the last one I'm going to use is 7/8. Sometimes these numbers that we have in here, we refer to those as x's with a subscript. So the 0 here, which is the furthest I can get left on this interval, we call that x0. 1/8 here would be the first one after that, which is x1. Then this would be x2, etc. The 7/8 would be our x7. Now, when we use a right-hand sum, we'll be using the right endpoints. So there is actually an x8 there, but we don't use it for a left-hand sum. x8 in this case would be equal to 1, or 8/8. Okay? But we're not going to use it because we're using the left endpoints only. And that's why we have to start counting at 0 instead of 1, so we still only get up to 8 for the 8 rectangles. All right. So our estimate then becomes the value of the function at 0 times the width, which is 1/8, the value of the function at 1/8 times 1/8, the value of the function at 2/8 times 1/8, etc., all the way to the last one. Notice that they all have the same width. It's a common factor, so I just remove it, and what's left over is just the values of the function added up at all these different places. So I'm going to add up the function values at all of those different places. All right, so if I'm going to do that, all I have to do is take y equals x squared, which was the function, and evaluate it at each of those spots, add them all together, and multiply by 1/8, and what I end up with is 0.27344. Now I know that that's not a great estimate. We lost a lot of area there, but it's reasonable, and we also know it's an underestimate, so that's less than or equal to what our area is actually going to be. Let's take a look at the right-hand sum. When I use the right-hand sum now, same process, only I use the other endpoint of each subinterval to find the heights of my rectangles, which means I don't start at 0. I actually start at 1/8 for my first x coordinate that I evaluate, and I go all the way to 8/8. So you'll see here, for my lengths, I start at 1/8 and go all the way to the end. So if I was labeling those, I don't start at x0 this time. I start at x1, and I go all the way to x8. So I use x8, but not x0. And then it's basically the same process. I multiply all those function values by 1/8 all the way through, factor out the 1/8, evaluate them all, add them all together, and this time I get an estimate of 0.39844. Now, what I know here is that that's too big, so this is actually an overestimate for the value of my area. I don't know what my area is, but I've ballparked it now. I know it's between about 0.398 and what was the other one we had, 0.273. So I don't know exactly what it is, but it's somewhere in that ballpark. Okay, so let's do an example here. One of the ways you get asked questions about Riemann sums is sometimes they'll ask you, here's a table of values with some values of f of x and at given values of x, and use the information here to estimate the area under the curve for the Riemann sum. And you think, well, I don't have a graph, but you don't need a graph. All you need are the points. So basically, I know that at 0, this function has a height of 20. At 0.5, 26, etc., all the way to the far endpoint on my interval 0 to 2, which is at 2, where the height is 38. Now we're asked to use both left and right Riemann sums here. So the left sum, and we're using 4 subintervals. So the left sum, L4, is going to be equal to, now we've got to figure out the width of all the intervals, our delta x, and that'll be the same for both sums. So the whole interval goes from 2 to 0, 0 to 2, so it's 2 minus 0 divided by the number of rectangles we're using, which is 4. So we've got a value of 1/2. Oh, I said 1/2 and wrote 1/4. 1/2 for our delta x. So I'll just leave that out in the factored form. And I know that when I boil all this down, I just take 1/2 and I multiply by all the function values added together for the heights. And if it's a left sum, then on the interval from 0 to 0.5, I use the value of the function at 0. And on the interval from 0.5 to 1, I use the value at 0.5. So I'm going to use the 20, the 26, the 30, and the 35. But I'm not going to use the 38 for my left sum because that's the height at the right endpoint of my last interval, and that's not part of the left sum. So I've got 1/2 here times, what do we got, 46 and 65, so that's 111. So I got 111 over 2 for my left sum. And for my right sum, our 4, it's going to be the same width, which is 1/2. Only instead of starting at 20, I'm going to start at 26 and use the right endpoints only. So 26 and 30, 35, and that was 38, I think, before I messed it all up there. Let's see. Yep, 38. Okay, so we got 38 there. So we add all that together and divide by 2. Let's see. That's 56 and 73, I believe. So 56 plus 73 is 123, 129. 129 over 2 for that one. So that means I don't know what my area is, but using left and right endpoint estimates according to Mr. Riemann, I know that it's going to be between 111 over 2 and between 120 and less than, 129 over 2. So I've given an upper and lower bound by estimating, and 4 rectangles is a pretty crude estimate, but at least I'm getting in the right vicinity for this now. Okay. More often you'll get questions that ask you to do Riemann sums, either left or right-hand sums, with however many subintervals, but they don't give you the table of values, they give you the equation, which basically means you've got to figure out the table on your own, more or less. Okay, so let's see if we can figure this one out. So it says they want a left-hand sum, 4 subintervals to estimate the area under this curve on the interval from 0 to 2. So let's first get our interval width. Delta x is going to be 2 minus 0, one endpoint minus the other, divided by, sometimes we call it n, the number of rectangles, but here we know it's 4. So that's 1/2. Again, I tried to write a quarter. So it's 1/2. And then I know that my left-hand sum with 4 subintervals is going to be that width of 1/2 multiplied by the function values all the way through. I better get rid of that last bracket because I think I'm going to need more space to write out what's going on with those function values. Okay, so the first one is going to be f of, our first one for the left-hand intervals here is going to be 0, plus, then we're going to have f of, it's going to have to be 0.5, because one interval width away from 0 will be at 0.5, then f of 1, and f of 1.5, which should be a half a unit shy of the right endpoint since I'm doing the left sum, which it is. So that's going to be 1/2 of, now f is our function that we defined over here, so that's going to be 2 times 0 squared plus 3, plus, we've got 4 of these now, 2 times 0.5 squared plus 3, plus 2 times 1 squared plus 3, and 2 times 1.5 squared plus 3. Put all that together, and I've got to figure out what this is going to give me for my total. So let's see. This is going to be 1/2 times, we're going to have 3 plus, that looks like about at 0.5. I'm going to get 3.5 there, right? So 3.5 plus, I'm thinking 5 and 7.5. So if I add all those together and divide by 2, I've got 6.5 plus 12.5, which is 19 over 2. So I get 19 over 2 there, and that's going to be my left-hand estimate. It's 19 over 2. Okay, let's go and do a right-hand estimate. Now I'm betting that's the next example because I made it up. And it is. Okay, so here we go. Use a right-hand Riemann sum with 4 subintervals to estimate the area. So it's going to be almost the same thing. So we don't want L this time, sorry, we want R4. R4 this time is going to be the same interval width, which was 1/2, times F, and I'm not going to start at 0 this time because it's a right-hand sum. I'm going to go 1 interval width in from 0. So I start at F of 0.5, then I add F of 1, F of 1.5, and I use the last one, which I didn't use before, which is F of 2. Okay, so that's going to be 1/2 of, we've got 2 times 0.5 squared plus 3, 2 times 1 squared plus 3. Going to run out of space with this stuff. And let's put them down here. So then we're going to have 2 times 1.5 squared plus 3. And of course we'll have 2 times 2 squared and 3, like so. And then we put all that together, so we've got 1/2 of, we should get 4 numbers here. I'm getting the 3 that we had before, 3.5, 5, and 7.5. And then this is going to be 8 and 3, which is 11. So we put all that together again. And we're going to have 11 plus 16. Does that sound about right? 11 plus 16 is 27. So our estimate on this side is 27 over 2. So there's our right-hand estimate for this particular example. All right, so that's how we do Riemann sums. Typically, if you're going to do them out by hand like this, no one asks you to do one with like 28 subintervals or 100 subintervals. Yuck. You get a better estimate, but it would take you a heck of a long time. All right. Your turn question. Use a Riemann sum with 4 subintervals. See how nice I am? To estimate the area under the curve, f of x equals 1 minus x squared on the interval from 0 to 1. Just a little bit of a note here you should probably do, because I did change it on the slide, the next one that has the solution on it. Try a right sum, because that's the one I want you to compare to the solution. So use a right-hand Riemann sum to do that. And you'll notice that because this is a graph that has its vertex at 0, 1, and it actually decreases over here. It's a decreasing function. First one we've looked at. A right-hand sum will actually give you an underestimate. See that? Whereas a left-hand will give you an overestimate. So whether the curve is increasing or decreasing will determine what you get with this stuff. Okay? So good luck with that. I'm going to jump to the solution, so if you want to pause and work it out, go for it. So there's your solution all worked out, and that's what we get using a right-hand Riemann sum with 4 subintervals. See, I did change it. Okay? And then we'll highlight some of the key features that we had here. So the area problem arose from an inability to compute the area under irregular 2D shapes, such as the area under a nonlinear curve on a finite interval. So one way we attempted to solve that problem was using a means of estimation, invented by a really, really old guy named Bernhard Riemann, and he called it the Riemann sum, or we did. I don't know who named it, but he invented it. So to actually compute, missing word should be compute a Riemann sum, we divide the interval into n subintervals. So note that we're using the letter n here because it's going to crop up in this formula down here in a sec. So we divide the region into, or the total interval, into n subintervals, and we draw rectangles, the top of which touch the curve at either the left or right endpoint. And the area is then estimated using the following formulae. This one right here, b minus a over n, that's just your delta x. And you find that by taking the length of the entire interval divided by how many rectangles you have. And then for a left sum, we add up all but the last endpoint, the function evaluated all but the last one. And for a right sum, we add up all but the first one. And then what that gives us is 2 different sums. One will overestimate, one will underestimate, and hopefully they get pretty close. And hopefully you're getting all of this and that you're going to do very well on your exam. If you have any questions, post them on D2L, please, and thank you.